Hello everyone and welcome back to ECS 2200. Today we're going to start with chapter 7, which is about first order RL and RC circuits. So in the previous chapter we talked about capacitors and inductors. We introduced them. We talked about their basic principles, their voltage and current relationships, their power consumption, and the energy that they store in themselves. And we learned how to basically combine them in series and parallel, how they're dual of each other, their behavior is kind of like dual of each other. And in the end, we learned about the concept of mutual inductance. In this lecture, we're going to learn about how to analyze, quite simple circuits that include one of the inductor or capacitor, as well as a bunch of other resistors and voltage source or current sources. So the circuits that we're going to be discussing in this chapter are going to be basically very similar circuits to to chapters 1 to 4, meaning that they have voltage source, current sources, and resistors. The only additional element to these circuits is that we're going to have either capacitor or inductor. We're not going to learn about circuits that have both of them until chapter 8. So for this chapter, we're just going to talk about the circuit that has one capacitor and a bunch of other resistors and sources, or one inductor and a bunch of other sources and resistors. And we're going to learn how to analyze these kind of circuits. And then, well, in chapter 8, we're going to continue our discussion to learn more about how to analyze circuits that have both of inductors and capacitors. So the first concept that we're going to talk about here is natural response of an RL circuit. Why natural response? Why we call this RL? You're going to learn that by the end of this slide, right? But for now, let's just focus on the circuit. Let's say that a circuit like this is given to us, and the question is telling us to find I and V, right? But the question is also asking us to find these two parameters for t greater than 0. Okay, so the circuit is quite simple. So it has a current source Is that is a constant value. It has a couple of resistors and one inductor. The only thing that might be actually a little bit new to you is the symbol of the switch and the annotation of t equal to 0. So what it really is telling us is that assume the present moment, meaning now, is t equal to 0, right? So the circuit, the annotation really is telling us that the circuit had a switch that was closed from negative infinity until now, until t equal to 0. And after, at the time equal to 0, we open the switch. So that's what the annotation means, right? At t equal to 0, we're opening the switch, okay? And we want to know what happens to the current and voltage that are shown here and here on the circuit. What happens to these currents and voltages after t equal to 0, okay? So that's the question. To answer that question, first we need to actually know, well, how does my circuit look like after t equal to 0, right? So after t equal to 0, I can see that the switch opens. The moment that switch opens, the two parts of the circuits are going to be kind of isolated from each other because there's no return path for the current. So there's no current going from left side. So if I draw this line here, there's no current going from the left side to the right side and right to the left, right? If this is not clear to you, go back to chapter 1 where we discussed the meaning of circuits and why we need a return path to have current flowing through a circuit, okay? So since V and I that I'm looking for are on the right side of the circuit, I'm just going to be basically drawing the right, I'm going to be analyzing only the right side of the circuit. So let me just erase all these annotations for cleanness. I'm going to have a simple circuit as this. So I'm going to have this R and I'm going to have this L. I is defined as this and V is defined as this one, right? And since I is actually moving clockwise, I'm going to define the voltage of the inductor as VL with this kind of polarity, right? Remember, the current is always flowing in the direction of potential decrease, right? Now, or potential drop. Now, let's analyze the circuit. It's a simple resistor and inductor kind of a circuit. That's pretty much why we call these RL circuits. The kind of circuit that we are analyzing is basically always it always contains one inductor L and one resistor R. It might be more than one resistor, but then we know how to combine more resistors into one using series and parallel combinations. So at the end, we're dealing with one resistor and one inductor for any of these kind of circuits. Okay. Now, if I want to actually analyze this, I'm just going to use the same tools that I always use, which is basically KVL and KCL. So if I write KVL here, I'm going to have, well, VL plus VR equal to 0, or negative VL minus VR is equal to 0, depending on which direction you go for your KVL. So VL is L di over dt. We learned that in chapter 6, and VR is Ri is equal to 0. So that tells me that L di over dt is equal to negative Ri. And by moving things around, I can get di over I is equal to negative R over L times dt. Okay, I brought it to this form because I wanted to take the integral to two sides, and for one side I'm taking the integral with respect to I, and for the other side I'm doing it with respect to t. So 1 over I, if I want to take the integral, I'm going to get ln of I, and it's from 0 to right now, so 0 to t, so it's going to be from so for I of t to I at 0. This is equal to negative R over L, which is a constant, times dt. Well, integral of dt is just going to be t, right? It's a constant. The integral is going to be just t. This tells me that ln of I t minus ln of I at 0 is equal to negative R over L times t, and that tells me that ln of I t over I at 0 is equal to negative R over L times t. Okay, I take the exponential function I apply the exponential function to both sides, so exponential and ln kind of cancel with each other. I'm going to get I t over I at 0 is equal to the e to the power of negative R over L times t. And that tells me that I t is equal to I at 0 e to the power of negative R over L times t. Okay, and I'm pretty much done. So I found current in terms of as a function of time, because well, t is time, so I don't care about that. R and L are the constant values of the resistor and the inductor. They're given. The only thing that is missing here is the current at time 0. So first I have to actually find that. I'm not completely done, but I found the equation that basically represents the behavior of my current, the current I, after t equal to 0, right? And well, finding the voltage V is actually quite easy, because I know that V is equal to Ri. So it's just going to be R times I0 e to the power of negative R over L times t. Okay, so that part was actually quite simple. So the only thing that is missing here is that finding the current at time equal to 0. Before actually talking about that, if you zoom out and look at this expression, we'll see that basically this circuit is telling me, these analyses are telling me that the current of my inductor and resistor, the current of my circuit, the RL circuit that I have after t equal to 0, is going to be a decaying exponential, right? So it's basically at time 0, if I put t equal to 0, e to the power of 0 is going to be 0, is going to be 1. So it's just going to be I 0, right? So at 0, I'm just going to have an initial constant value. And then as I go forward in time, what I'm going to get is basically this initial value is just going to decay. And this behavior is actually shown here. So you have this I0 in the beginning, and after that, you're just going to have a decaying exponential. You never get to an absolute 0, but you get pretty damn close to it. Okay, so that's the behavior. And now I have to think about how do I find this I0, right? How do I find the current at time 0? Well, to do that, my guess would be, well, it has something to do with the behavior of the circuit before time equal to 0, right? If I want to find this thing, well, whatever is happening after t equal to 0 is not going to affect the current in the past, right? So we are only affecting the current, the parameters in the future. So it's better to actually analyze the behavior of the circuit before t equal to 0, okay? So if I want to actually, if I want to analyze the circuit before t equal to 0, basically I just have to redraw the circuit that I had, with one exception that the switch is closed, right? So I have the entire schematic, not just half of it. So I have my R, my L, the R0, and IS, okay? And what I'm really interested in is, well, finding the I before t equal to 0, right? To analyze the circuit, I need to actually go back to my knowledge from chapter 6, right? If you remember from chapter 6, we were, one thing that we said about inductors was that if you have an inductor and there's no change in the circuit, the voltage of the inductor is going to be, the voltage across the inductor is going to be 0, right? Because we know that voltage of an inductor is L di over dt. So if I have a circuit that there's no change happening in it, and I know that from the circuit schematic, from the question, is telling me that from time equal to negative infinity until t equal to 0, so for a long time, nothing has happened to this circuit. The switch was closed, my source is constant, and the value of resistors and inductors are not changing for sure. So nothing is really nothing has happened to this circuit. So the voltage across my inductor is definitely 0, because di over dt, which is really representing change, the rate of change in the current, is going to be basically 0, right? So it doesn't matter what is the value of the inductance that I have here, my VL is going to be 0. So, or another way to actually think about this is that because there was no change in the circuit for a long time, and by long time we mean from negative infinity until 0, right? Because there was no change in the circuit, I can actually redraw my circuit as R0, and then instead of R, I'm just going to put R. Instead of L, I can just put a wire. Remember we said that a coil, an inductor, is just basically a coiled wire. It's just basically a wire wound kind of shape, kind of a thing, right? So if there's no change, it's a piece of wire. There's no, basically there's not going to be any kind of voltage across this, and so it's going to be simple. It's going to be basically similar to an ideal wire which doesn't have any voltage across it, right? Okay, my circuit just got very interesting, because now I know that I have a short circuit that is basically in parallel with two resistors. Now I don't care what is the value of these resistors. I know that whatever current IS that I have here that is flowing through this branch, when it gets to this node, remember this and this and this are the same node, right? When it has to be divided between the short circuit, the branch that has R0, and the branch that has R, well, it's going to choose this branch, the short circuit branch, because, well, it's not stupid. It has the least amount of resistance, zero resistance against the movement of charge carriers, right? So the current here is going to be IS. Okay, so that is what I can actually tell from analyzing the circuit before t equal to 0, right? So this tells me that IL, the current of my inductor for t less than 0, is going to be equal to IS. Great. Okay. So why did I care about the current of inductor? I didn't go and look at any other current, like current of a resistor or voltage of inductor or voltage of resistor. There was something, if you remember from last chapter, and if you don't, go back and, well, review it. If you remember, there was one parameter about the inductor and one parameter about the capacitor that we called them golden parameters. For the inductor, we said current of the inductor is golden parameter. For capacitor, we said voltage of a capacitor is the golden parameter. Why we called them golden? The reason was that they cannot have any instantaneous change. They're gonna have a continuous behavior, meaning that if I'm looking at the value of this current of an inductor at this moment and a moment from now, the difference is not going to be anything but 0, right? So like if I just basically reduce or like basically make my time steps as small as an epsilon, I'm going to make sure that there's a current, like there's a continuity in the value of these parameters, the current of an inductor and the voltage of a capacitor. So how do I use this? So like I cannot say this about like basically we discussed that and we show it by example that I cannot say that about like the current of a resistor, right? Or like basically voltage of a resistor or voltage of an inductor or any other parameter other than current of an inductor or voltage of a capacitor. I cannot stress this enough. So why did I talk about this? Because when I can say IL at t less than 0 is equal to IS, this means that IL at t equal to 0 minus is equal to IS. What do I mean by t equal to 0 minus? I mean just before the switch was opened, right? Like 1 epsilon, 1 picosecond, 1 femtosecond before the switch was open. Just one moment before the switch was open, I can say that the current of the inductor was IS. And then because of the continuity, because of IL's continuity, I can say that IL at 0 plus is also equal to IS. Okay, so just after I open the switch, after that it can whatever you can imagine could happen to it, but just after I open the switch, it's going to remain at IS. I cannot say that about, like, for example, current of the resistor or voltage of the inductor or voltage of the resistor, right? You can see that, like, basically the current of the resistor just before the switch was opened was basically the current of, for example, let me use a different color. What I'm talking about is this resistor, for example. The current of this resistor just before the switch was open was 0, right? Because all the current was going through the short circuit. How about after t equal to 0? Well, we just found it. It was actually this. So it becomes equal to the current of the inductor. They have the same current because they're in series, right? Because of this circuit. So the current of the resistor jumped from, like, if I wanted to plot the current of the resistor, it would have looked like exactly like it was 0. And then at time equal to 0, it jumped all the way to this point. And then it had the same behavior as the inductor. So IR. Okay. How about the current of the R naught, this resistor? Well, before t equal to 0, it was 0. after t equal to 0, it becomes is. Why? Because, well, we divide the circuit into two parts. When the right part is gone, all of this current is going to flow through this R0, right? So it becomes is. So again, you can see that we have these instantaneous changes in the current of any other element, or if we discuss the voltages, we're going to see the same thing, right? They don't, like, basically, if we look at any of these things, we're going to see that we have these instantaneous changes except for the current of an inductor, and then later we'll see the voltage of a capacitor has the same property. So based on all these analyses, this tells me that I at 0, because it's the same, this I is actually flowing through the inductor as well. So I at 0 is going to be the current of the inductor, and it's going to be is. Therefore, my IT, the current as a function of time, is going to be is times e to the power of negative r over L times t. Okay, so now I have everything because is, r, and L are given. So I have my current after t equal to 0 as a function of time, and voltage is just going to be r times that. So I'm not going to even write that. Okay, so I hope this was clear. So what we did as a recap was that first we analyzed the circuit's behavior after t equal to 0, right? We wrote the KVL and we found the relationship between the current and, like, well, not the relationship. We found the expression for the current as a function of time. We saw that it's a decaying exponential. We knew it's a decaying exponential, we just didn't know where does it start? What is the initial value? To find that initial value, we kind of resorted into the to this amazing property of the current of an inductor, that it has a continuous behavior. So we know that before and after switching, it's going to be the same, right? So think of it as two different eras, right? So like the era of after switching and the era of before switching. The only thing that is connecting these two time zones is really the current of an inductor. Anything else could change at the time of switching drastically. The only thing that remains constant before and after switching is going to be the current of an inductor. So we found the current of an inductor immediately before the switching happened, and then said that, well, this current of an inductor is equal to the current of an inductor immediately after switching, and I'm going to use that to find, well, the initial value of the current. In this case, the current of an inductor and the current that the I that I was looking for are the same thing, so I was lucky, so I just said I is equal to is. We're going to see examples where we're just going to use the current of an inductor to find the initial value of some other parameter. We're going to see that in the future, okay? The last thing they promised that I'm going to talk about, and I haven't yet, is why we call this natural response. We said that why we call it RL circuit, but we didn't say why natural response. Well, this is mainly because we are analyzing a circuit that was connected to a source, and after the switching happens is not connected to any kind of a source. The circuit that we are analyzing, the RL circuit that we are analyzing here, is just basically a resistor and an inductor, right? So you might think that, well, a resistor and an inductor, they shouldn't really have any kind of like current. There's no source. There shouldn't be any current or voltage. Well, that's kind of true if it was only resistors, right? But one thing that we know about inductors and capacitors is that they can actually store energy for a limited amount of time, right? And that is why we have a little bit of a transient behavior. You see that it becomes zero after a while, right? So it's not going to be like if you leave a resistor and an inductor with each other on the table connected, they're not going to have any current or voltage after a long time, right? We're just talking about the transient behavior of the circuit right after disconnecting it from a source, right? So it's kind of like a natural response of this R and L when there's no source involved. That's why we call it a natural response, because there's no source is involved in this process, right? Later we're going to talk about step response when there is a source involved, right? But for now we're talking about natural response, and because there's no source involved. One other thing that I've seen students asking is that, well, I mentioned that this when I was actually analyzing this circuit here, this one. So when I was analyzing this, I mentioned that since this circuit has been around for a long time and there is no change in it, then I can actually say that the inductor is a piece of wire, so I can actually replace it with just an ideal wire, right? You might say, well, why don't you do, like, basically we don't have any change in this, like why didn't you say the same thing about this circuit and the inductor here? If you think about it, we did have a change recently. We did have a change at t equal to 0, and that's why the inductor has a voltage across it, right? But if you think about it, after a while, this voltage, you can see that this voltage, because the voltage across the inductor is equal to negative of the voltage across the capacitor, right? So if IL is equal to this expression, you can imagine that V of L is going to be just basically negative R times that. So we know that the voltage across the inductor is also going to be a decaying exponential. So after a while, it is going to be 0 because, well, we had one change in this circuit at time equal to 0, and that change caused some transient behavior. But then after a while, because there's no change, the voltage across the inductor, intuitively, it has to be 0 at the end at time equal to infinity, and it becomes 0, right? It gets closer and closer to 0. Okay. I hope this was clear. We're going to solve so many examples of these RL and RC circuits until it's fully clear for all of you. Okay, so one thing that we need to actually clarify is this concept of long time, right? You remember that when I said before switching, there has been a long time that there hasn't been any change in the circuit, right? Or after switching, if you wait long enough time, the voltage of the inductor and the current of the inductor, everything becomes 0, and I just have one resistor and inductor connected to each other without any kind of activity in there, right? So what is this long time, right? Is it 1 millisecond, 1 second, 10 seconds, 1,000 seconds? How long I have to wait? The answer is, well, it pretty much depends on this circuit, right? So if you can think about it. If you have think about capacitors because they're more intuitive. If you have a big capacitor, right? Kind of like a big battery. Think of it as capacitor and batteries are like very similar in many ways, right? If you have a big battery and you're discharging it, if somebody asks you, well, how long it takes for this battery to be discharged, you would say, well, it depends on the size of the battery, number one, and how fast, like if you're, for example, if I'm talking about the battery of a cell phone, how many applications have I have open, and basically how power hungry these applications are, and so on, right? So it depends on the size of my energy storing component, which is the battery or the capacitor or the inductor, and the rate that I'm burning energy, which is really the R, right? So the higher current they have, the higher my R is really burning energy, it's consuming energy, it's wasting energy, right? So the higher current it's going to have, the faster it's going to burn the energy, right? So it has something to do with L and R for an RL circuit, and it has something to do with R and C for an RC circuit that we're going to talk about later, right? For example, for the previous circuit that we just discussed, we got I of t is equal to some initial current, let's call it I naught, right? We found it to be Is for that specific circuit, times e to the power of negative R over L times t, right? Now let's define tau here as a time constant. We're going to call it time constant, and we're going to define it as L over R. So here we had R over L, we're going to define this as L over R. So I can rewrite IT as I naught e to the power of negative t over tau, right? So because it's 1 over tau, right? So now if I start to analyze this negative t over tau and only look at this part, right? Because this is only look at the exponential part, because this is really a constant, right? If I look at the exponential part and I look at this table, I can see that for tau, for 1 tau, e to the power of t over tau, so if t is equal to tau, right? E to the power of negative t over tau is going to be equal to e to the negative 1, which is equal to 3.67 times 10 to the negative 1. Then for 2 tau, I'm going to have e to the power of negative 2, and all the way to, let's say, 5 tau, I'm going to have e to the negative 5, right? So I'm just replacing t with a tau or 2 tau or 3 tau or 4 tau or 5 tau, right? I can see that if I have an initial value, let's say this initial value of I naught could be 5, 10, 50, whatever, right? At t equal to tau, I'm gonna have, so 3.6 times to the negative 1 is like 0.367, right? That's like 36% of the initial value, right? So basically at t equal to tau, it is going to be equal to I naught times 0.367. So 36.7% of my initial value. At t equal to 2 tau, this is going to be 13%. So 0.135, so it's going to be 13.534% of my initial value, right? If I continue this, at t equal to 5 tau, I'm going to get to 10 to the negative 3, right? So this is going to be 0.67% of my I naught, right? So I can say that after 5 time constant, I'm going to get to less than 1% of my initial value. That is good enough for us engineers to approximate that as, well, after this, pretty much no change is going to happen. You can look at it. From 5 tau to 10 tau, I'm going from 0.67% to 0.00 something percent, right? So like basically the rate of change is going to be just negligible, right? So I can say that after 5 tau, after 5 time constant, there's not going to be any significant change in my current. Therefore, I can kind of assume that my circuit is constant. So this 5 tau is really the definition. So this is the approximate definition of what we call long time. So when I say a long time has passed for the circuit, I mean that, well, look at the circuit, look at L and R, and calculate the time constant. And then basically you can say that after 5 tau, 5 time constant, you can say that it's been a long time. So there's no, you can safely say that there's no change happening in this circuit anymore. Okay? So that is what we mean by long time from now on. And what by time constant of an RL circuit, we always mean L over R. Okay? Okay, so let's solve an example. Let's say that this circuit is given to us and the question is asking us to find IT for t greater than 0. So in some sense, it's very similar to what we have already discussed up to now, meaning that at t equal to 0, the switch opens. So my circuit is kind of divided into two parts. The part that I care about, which is on the right side, why do I care about the right side? Because I is in that side. So the part that I care about is just basically a resistor and an inductor, right? The values are given and might be different from what I've seen before, but at the end of the day, it's the same circuit. So I don't even need to actually write all those parameters, right? All those equations to get to the form, the decaying exponential form. I know that I, which is the current of the inductor, IT. So for t greater than 0, I know that IT is going to be basically I at time 0, e to the power of negative R over L times t. Okay. Now, what is R? R is 2 ohms, and L is 8 millihenry. Sorry. So R over L is going to be 2 times 8 times to the 10 to the negative 3. So this is 2000 over 8, which is equal to 250. Okay, so this is going to be, therefore, IT is going to be I at 0, e to the power of negative 250 t. Okay, so the only remaining part would be finding that initial condition, finding the initial value of the current of the inductor. Okay, so we know how to do this. We know the drill. I just need to actually analyze the circuit before t equal to 0. So for t less than 0, I know that my circuit looks like this. So the voltage source, the 120 volt voltage source, I have my 3 ohm resistor, I have my 30 ohm, the 6 ohm, and inductor and resistor, right? So I just replaced the switch with a piece of wire because the switch was closed before t equal to 0. Now, again, I know that before t equal to 0, for a long time, since negative infinity up to now, and up to t just before switching, the circuit hasn't changed, and it's a constant source, so my inductor can be replaced with a piece of wire. So I'm going to do that. So I'm going to replace that with a simple piece of wire. So there's no inductor anymore. I'm just going to, well, not going to erase it. I'm just going to put a cross on it, right? So now that I have this, I can simplify my circuit to, does it mean that like all my resistors are going to be gone? Of course not, right? Those resistors in the previous example were gone because they were in parallel with my inductor. In this case, the only resistor that is in parallel with the short circuit is the 2 ohms, and I'm going to get rid of that. But anything else is going to stay. So this is my 6 ohm, and I'm going to have this short circuit. And I'm going to get rid of the 2 ohm because, well, it's in parallel with the short circuit. So it's not going to get any current. It's not going to affect my circuit. Now, I know that I'm looking for, still I know, although I replaced my inductor with a short circuit, I know that the current of inductor is here. So this is the I that I'm looking for, right? So how do I find the I? Well, this is the circuit cannot get simpler than this, right? It's just basically a bunch of resistors that we know how to deal with them. So I would say 6 and 30 are in parallel. So 6 is in parallel with 30. So this is equal to 6 times 30 divided by 6 plus 30, 36. So that's 180 divided by 36. That is 5. And 5 and 3 are going to be in series. So I'm going to have an 8. So if I define this current, let's call it I source IS. IS is going to be equal to 120 divided by 5 plus 3. So 8. So 120 divided by 8, I'm going to get 15. So I'm going to have 15 amperes as the IS. And then IS is going to be divided between the 6 ohm and the 30 ohm in a current division kind of a thing, right? So let's call this I1. So I1 is going to be 30 over 30 plus 6 times 15. So that's basically 30 over 36, or 5 over 6. 5 times 15 is 75. Divided by 6, I'm going to have 12.5. Okay, so I'm going to have a 12.5 amperes flowing in the I1 direction. Therefore, I is for t less than 0 is going to be equal to negative 12.5. And that's it, because now I found the current of my inductor to be negative 12.5 amperes just before the switching happened. So I know that, so I at 0 minus is equal to negative 12.5 amperes. Therefore, I at 0 plus is going to be equal to negative 12.5 amperes. Therefore, I can say that IT is equal to negative 12.5 times e to the negative 250 t. And that's it. I found the relationship between, or the current of my inductor as a function of time after t equal to 0. Okay, so just to recap, how did we approach this? We saw that this is a natural response RL circuit. Why? Because the moment that we considered the circuit after switching, we saw that we are left with a resistor and an inductor, and there's no source. So it is natural response because there's no source, and it is an RL circuit because, well, there's an R and there's an L, right? So the moment I knew that the behavior of my circuit is going to be a decaying exponential with initial current here and e to the power of negative r over L times t as the other term in that expression. I knew that what is r and what is L, so I wrote the expression like this. The only thing that was missing was the initial condition. To find the initial condition, I went back in time and looked at the circuit before t equal to 0. I simplified the circuit. I considered the fact that the circuit hasn't changed for a long time, so I can replace the inductor with a short circuit with a piece of wire. I simplified the circuit to this form, and I calculated the current. And I knew that the current at t equal the current of an inductor, basically not anything else, current of an inductor, because it's a golden parameter that we have defined before, immediately before and after switching is the same. So I used that property to find the initial current that I was looking for, this I0, right? And then I wrote the expression. Now, if you want to practice this, and I do encourage you to do that because you might see different kind of circuits before and after switching, go and practice with examples 7.1 and 7.2. The solutions are given in the textbook, but well, as always, I encourage you guys and strongly recommend not to look at the solution. Just do it yourself, get to the answer, and then look at the solution and try to see where did you go wrong. That's the only way that you can actually learn circuits. By reading the solutions, you're not going to learn anything.